exercise questions of chapter Thermodynamics. Question 1. A geyser heats water flowing at the rate of 3 liters per minute from 27 degrees Celsius to 77 degrees Celsius. If the geyser operates on a gas burner, what is the rate of consumption of the fuel if its heat of combustion is 4 into 10 power 4 joule per gram? Look at the data given in the question. We have heat of combustion is 4 into 10 power 4 joule per gram. Specific heat of water is 4.2 joule per gram per degree Celsius, and the mass of water is 3 liter per minute, that is 3000 gram per minute. The initial temperature and final temperatures are given. Therefore, we can calculate the change in temperature delta T. Change in temperature delta T is equal to 50 degree Celsius. Now, what is the amount of heat absorbed by the water? We can use the formula delta Q is equal to ms delta T. Delta Q is equal to ms delta T. So you can substitute the values in SI unit. When you substitute the values in SI unit, the mass of water is given as 3000 gram per minute. Therefore, we can have 3 into 10 power 3. Then specific heat of water is 4.2. Change in temperature is 50 degree Celsius, so that we get the amount of heat absorbed in joule per minute, because the mass is given as 3000 gram per minute. Now, from 1 gram of fuel, we get the heat 4 into 10 power 4 joule per gram. Therefore, the amount of heat absorbed we can calculate as the rate of combustion of the rate of consumption of the fuel. That is, rate of consumption is equal to rate of consumption of the fuel is equal to 3 into 10 power 3 into 4.2 into 50. So it is better to write the unit also to avoid the confusion. Joule per minute upon the heat produced per gram of the fuel, that is 4 into 10 power 4 joule per gram. Here you can see the joule, the unit joule is cancelled in numerator and denominator. Gram goes to numerator, so that the final result you get in terms of gram per minute. And when you simplify, your answer will be approximately 15.7 gram per minute. 50.7 gram per minute. Now, question number 2. What amount of heat must be supplied to 2 into 10 power minus 2 kilogram of nitrogen at room temperature to raise its temperature by 45 degrees Celsius at constant pressure? Molar mass of nitrogen N2 is equal to 28 and gas constant is 8.3 joule per mole per Kelvin. So we have 2 into 10 power minus 2 kilogram. 2 into 10 power minus 2 kilogram nitrogen. Now from this we can calculate the number of moles of hydrogen. How can you calculate the number of moles? Number of moles is equal to mass of hydrogen upon its molar mass, and molar mass is given 28 gram, and mass of hydrogen is given 2 into 10 power minus 2 kilogram. That is 2 into 10 power minus 2 into 10 power 3. So you will get the answer 20. So mass of hydrogen will be 20 and molar mass is given 28 gram, so that the number of moles can be calculated. Once you get the number of moles of hydrogen, then we can have the specific heat of hydrogen, Cp, specific heat at constant pressure, is equal to 7R by 2. 7R by 2. So by substituting the values, okay, you can calculate the specific heat at constant pressure for hydrogen. Then afterwards you can use the formula for heat absorbed. Q is equal to NCP delta T. Q is equal to NCP delta T, where N is the number of moles, Cp is the specific heat, and delta T is the change in temperature. The question says that the rise in temperature is 45 degrees Celsius. So you substitute the values, simplify, you get the answer, the amount of heat required to supply, and you will get the answer approximately 934 joule. Now next, question 3. Explain why part A, two bodies at different temperatures T1 and T2 is brought in thermal contact do not necessarily settle to the mean temperature T1 plus T2 by 2. We know that heat absorbed or heat lost by a body, we have the formula Q is equal to ms delta T, where m is the mass of the object, s is the specific heat, and delta T is the change in temperature. Therefore, the heat absorbed or heat lost depends on mass of the object and specific heat of the object. The question doesn't tell anything about the masses of the two bodies and their specific heats. If mass and specific heat of both the bodies are equal, then we can say the change in temperature will be same. Therefore, the temperature will be the mean temperature of the two bodies, so that you get the resultant temperature when they settle, it will be T1 plus T2 by 2. But if the mass of the bodies are different or the specific heat of the bodies are different, then it is not possible to get the temperature T1 plus T2 by 2. According to the mass, according to the specific heat is high for a body, then for that body the change in temperature will be less. Similarly, if the mass of the body is high, if the one of the bodies is having high mass, then its change in temperature will be less. Therefore, it is not necessary you have to get the mean temperature T1 plus T2 over 2. That will happen only when both the bodies are having same specific heat and mass. Come to the part B. The coolant in a chemical or a nuclear plant, that is the liquid used to prevent the different parts of a plant from getting too hot, should have high specific heat. So you can see again So application of the same equation, Q is equal to ms delta T, and according to the equation, if the specific heat S is high, then change in temperature delta T is small. Therefore, if you want to keep the temperature low, the change in temperature low, we have to use a substance having very high specific heat S. When S is high, delta T is small. So that's the reason a coolant, okay, that we use to keep the temperature low, or if we want to transfer the heat from one place to another place, for all such substances generally we call the name coolant, and it should have high specific heat so that the change in temperature delta T is small for the substance on absorbing heat energy Q. Then come to part C. Air pressure in a car tire increases during driving. We know P proportional to T. During driving, due to friction, the temperature of the tires will increase. When the temperature increases, pressure also increases, because pressure is directly proportional to temperature for a given mass of gas at constant volume. So that is the reason air pressure in a car tire increases during driving. Now come to part D. The climate of a harbour town is more temperate than that of a town in a desert at the same latitude. So we know that our body temperature is controlled by sweating, the evaporation of sweat from our body. So once we have sweat on our body, what happens there? The water drop will absorb heat energy from our body to be evaporated, so that much amount of heat will be lost from our body, so that we can control our body temperature. Now you take the case of a harbour town. In a harbour town, the humidity is high. As humidity is high, the air contains lot of water vapor. Therefore, the rate of evaporation of the sweat from our body is comparatively less. So as the body finds difficulty to evaporate the sweat, then it is not easy to remove the heat energy from our body. Therefore, what happens? So it is difficult to remove the heat energy from our body so that we feel hot. Therefore, if it is in a harbour town, then we feel a temperature which is actually greater than the actual temperature. Or in other words, we say we feel more temperate in a harbour town. Then, question 4. A cylinder with a movable piston contains 3 moles of hydrogen at standard temperature and pressure. The walls of the cylinder are made of heat insulator, and the piston is insulated by having a pile of sand on it. By what factor does the pressure of the gas increase if the gas is compressed to half of its original volume? The question says that the final volume V2 is equal to half of the initial volume, that is V1 upon 2. Now you can observe the cylinder and the piston, everything are completely insulated. Therefore, the process that you obtain, as explained in the question, is an adiabatic compression. So we can take the initial pressure P1, final pressure P2, initial volume V1, final volume V2, and it is hydrogen, which is a diatomic gas. Being a diatomic gas, the ratio of specific heat gamma is 1.4, and we can use the characteristic equation for adiabatic process, that is P1 V1 raised to gamma is equal to P2 V2 raised to gamma. Now let's take the ratio of pressure. We have P1 upon P2 is equal to V1 P1 upon P2 is equal to V2 upon V1 the whole raised to gamma. Again, value of V2 is V1 by 2. Therefore, we can have V1 by 2 into V1 the whole raised to gamma is equal to 1 by 2 raised to gamma. Let's take the reciprocal of the equation. You will get P2 by P1 is equal to 2 raised to gamma, that is 2 raised to 1.4. So from that the ratio can be calculated and you will get the answer approximately 2.64. Now next, question 5. In changing the gas, in changing the state of a gas adiabatically from an equilibrium state A to another equilibrium state B, an amount of work equal to 22 joule is done on the system. Question says it is an adiabatic process. Then, if the gas is taken from the state A to B, from A to B, by a process in which the net heat absorbed by the system is 9.35 calorie, how much is the net work done by the system in the latter case? In the second case, we don't know what is the nature of the process, but in the first case, it is an adiabatic process, and in an adiabatic process, we know the amount of heat absorbed dQ is equal to 0. And use the first law of thermodynamics. You have dQ is equal to du plus dW, and dQ is equal to 0. No heat is absorbed being an adiabatic process, so we can say 0 is equal to du plus dW, which means the mode of du, the amount of change in internal energy, is equal to the mode of dW worked when the system changes from initial state A to final state B. Now, let's consider the second process. The second process, we have to calculate the amount of work done, and again we can use the first law of thermodynamics. We have dW is equal to dQ minus d. Now dQ is given in the question, it is 9.35 calorie. So, and the conversion formula is also given. So we have 9.35 into 4.19 is the amount of heat absorbed minus dW. So look at the first adiabatic process and the second process. In both the cases, system changes from A to B. As the system changes from A to B in both the processes, the change in internal energy is same. That is, the change in temperature is same for both the processes. As the change in internal energy is same, then we have already calculated the change in internal energy in adiabatic process, which is equal to the work done, and that is given in the question, 22.3 joule. Therefore, the change in internal energy du is equal to the work done in the first process, that is 22.3 joule. 22.3 joule. So that you get the answer. The work done in the second process is 16.9 joule. Now, question 6. Two cylinders A and B of equal capacity are connected to each other via a stopcock. A contains a gas at standard temperature and pressure. B is completely evacuated. The entire system is thermally insulated. The stopcock is suddenly opened. Answer the following question. Okay. So here, in fact, we have a cylinder. You can just draw like this, the cylinder. Now the cylinder has a partition. Cylinder has a partition, so that two compartments are there. Those compartments are mentioned as A and B. And the compartment A consists of a gas. Now what happened? The stopcock, which separates the compartments, is suddenly opened. As it is suddenly opened, then what happens to the gas? Now the gas has more space to occupy. The gas will expand, which we call the name diffusion process. We get the diffusion of gas from A to B. But at the same time, though it expands, in this case there is no work, because it is only a spontaneous process, a spontaneous expansion. Now come to the questions. Part A, what is the final pressure of the gas? You can see the final pressure of the gas becomes P by 2, half of the initial pressure. What is the reason? Because the volume of the gas becomes double. Then part B, what is the change in internal energy of the gas? So gas in this process, though we get expansion, I told there is no work. As there is no work, okay, there is no change in internal energy. So no change in internal energy of the gas. The gas retains its internal energy as it is a spontaneous expansion without involving any work. Then part C, what is the change in temperature of the gas? The same way, as there is no change in internal energy, we can conclude there is no change in temperature in this process. Then part D, do the intermediate states of the system before settling to the final equilibrium lie on PVT surface. We can see there this process is a rapid process. Being a rapid spontaneous expansion, there is no case of equilibrium during the process. Therefore, we can say the intermediate states in a rapid process, in a spontaneous process, okay, it's not at all at equilibrium during the process. Now, question 7. An engine delivers 5.4 into 10 power 8 joule of work per minute. That is, the work per minute is 5.4 into 10 power 8 joule per minute, and serves 3.6 into 10 power 9 joule of heat per minute from its boiler. That's the amount of heat absorbed from the boiler is 3.6 into 10 power 9 joules per minute. What is the efficiency of the engine and how much heat is wasted per minute? The efficiency of the engine, we can have the formula for efficiency. Efficiency is equal to useful work obtained upon heat absorbed. So we have the useful work obtained, already it is there, 5.4 into 10 power 8. That is a useful work obtained. And the total heat absorbed, we have 3.9 into 10 power 9. 3.9 into 10 power 9. So when you multiply into 100, so you will get the efficiency in percentage, and you will get the answer around 15%. Now, how much amount of heat is wasted in this process? So we can see the heat wasted. So if amount of heat Q1 is absorbed, then this Q1 is used to perform work plus the heat wasted Q2. Therefore, heat wasted Q2 can be calculated. Q2 is equal to Q1 minus W. So you will get, when you substitute the values, you will get the answer around 3.1 into 10 power 9 joule per minute. Now, question 8. An electric heater supplies heat to a system at a rate of 100 watt. 100 watt means you can take as energy per second. If system performs work at a rate of 75 joules per second, at what rate is the internal energy increasing? So again you can use the first law. We have dq is equal to du plus dw. Now in the question all these quantities were given per second, that is the heat supplied per second. So joule per second, that is 100 watt. Increase in internal energy per second, which we need to calculate, and work obtained per second, which is given in the question as 75 joules per second. So from that you can calculate the increase in internal energy per second, that is du per second is equal to dq per second minus dw per second. So substituting the values, okay, you will get the answer. It is 100 minus 75, that is 25 joules per second or 25 watts. Then question 9. A thermodynamic system is taken from an original state to an intermediate state by linear process. Graph is given, the PV diagram is given, then its volume is then reduced to the original value from E to F, that are shown in the diagram by an isobaric process. Calculate the work done by the gas from D to E to F. So it is a cyclic process, and the work done is obtained from the area of the cyclic process. So area you can calculate here. Work done is equal to area of the loop. Work done is equal to area of the loop in a cyclic process. So that is equal to, it is the area is traced in the form of a triangle. So half into the height of the triangle is 600 minus 300. So that is 300 into the base of the triangle is 5 minus 2, that is 3. So you get the answer. The work done in the process is 450 joule. Now question 10. A refrigerator is to maintain eatables kept inside at 9 degrees Celsius. If room temperature is 36 degrees Celsius, calculate the coefficient of performance. Now here we have to use the formula for coefficient of performance, that is beta is equal to, coefficient of performance, beta is equal to Q2 upon Q1 minus Q2, which is equal to, we can change in terms of temperatures, T2 upon T1 minus T2. So substituting the values, so you will get 282 upon 309 minus 282. You will get the answer 10.4. So these are the exercise questions and their solutions from the chapter Thermodynamics. Thank you.